Roberto Maiolino, who's also a good friend and collaborator. So Roberto graduated at the University of Florence, and during his PhD, he spent some time at the University of Arizona. And then he was a postdoctoral fellow at the Max Planck Institute for Extraterrestrial Physics in Quenching. And he soon got his first permanent position as a researcher astronomer at the Arcetri Astrophysical Observatory in Florence, where we actually met many years ago. After a few years, he moved as a senior astronomer at the observatory in Rome, and in 2012, he was appointed professor of experimental astrophysics at the Cavendish Laboratory of the University of Cambridge, and he was the first Italian to have a chair in the physics department of the University of Cambridge. And since 2016, he's director of the Kavli Institute for Cosmology. And in 2019, he became honorary professor at the University College of London. And since this year, a Royal Society Research Professor. So among the many awards and honors, he received also the knighthood from the Italian President of the Republic. So Roberto is primarily interested in understanding the mechanisms responsible for the formation and evolution of galaxies and their supermassive black holes, which he investigates using multi-wavelength observations. And within this context, he's member of the science working group of the James Webb Telescope and member of the Can I ask all of you to stop your mic?
Palestrato, perché vi ricordo che una volta questi passavano in consiglio di dipartimento.
Alberto Franceschini che ha il microfono acceso.
Sì. Non so, forse mi può aiutare a spegnerlo?
Sì, è mutato.
Ok, grazie. Thank you. So, so he's member of the science working group of the James Webb Space Telescope and member of the core instrument science team, NIRSPEC, and he's co-PI and project scientist of MOONS, the next generation multi-object spectrograph for the VLT, and also project scientist of IRIS, the high resolution spectrograph for the ELT. So today he will give us an overview of the many interesting results that he and his group have obtained within the context of an ERC Advanced Grant project on the quenching of galaxies and especially on the still missing pieces of this very complex puzzle and how we might be able to tackle these with the next generation of observational facilities. So thank you, Roberto, for accepting our invitation, and now I leave the stage to you.
Thank you, Rafa. Thank you also to the organizers for inviting me. Yes, I will try to give an overview of the quenching of subformation galaxies, which is currently a very hot topic, and I will try to explain you why it's so important and so interesting now. Just to clarify that I will not only be showing the results of my team, but more broadly, try to give a broader overview across also results from other groups and in the recent years. Okay, so just to, sorry, okay, this is interesting. We start.
È maledetto questo seminario.
Okay, so can you see the second slide? Because sometimes, okay.
Yes.
So this is a quick overview of the what we think is the formation, the process of evolution and formation of galaxies across the cosmic epochs. And what we know is that star formation peaked around 10 billion years ago, and during this lengthy period, the larger fraction of baryons were locked into stars. And but eventually, during this very lengthy process, only about 7% of the baryons made it into stars. So the overall efficiency of star formation in the universe has been very low. That's why recently it's become actually more interesting and actually more difficult to understand not only how stars form, but actually why stars haven't formed. Okay, so this is actually one of the main topics of research in many groups and many institutes. Now, we know that starting from the primordial fluctuations, dark matter has collapsed to form dark matter halos and dark matter filaments, and in these halos, baryons have accreted and cooled and formed gravitational collapse, forming galaxies and stars. And this snapshot from a cosmological simulation shows this distribution of galaxies in dark matter halos. However, this inefficiency, global inefficiency in forming stars in galaxies is not evenly distributed across all kinds of halos. We know that these processes have been particularly inefficient in low mass galaxies and in high mass galaxies, and this is summarized in this kind of diagram that many of you have probably already seen several times, where the blue curve shows the mass function of the stellar mass in galaxies, while the dashed red curve shows what we think is the dark matter halo mass distribution based on theory and on cosmological simulations. If this inefficiency in forming stars was uniform across all kind of galaxy masses, we would have expected that these two curves should have been more or less parallel. Instead, you see that clearly the process of forming stars has been particularly inefficient in low mass galaxies and in high mass galaxies. And typically, you see that I've taken this figure from another paper from 2013. Typically, the inefficiency in low mass galaxies is ascribed to supernova feedback, while the inefficiency in high mass galaxies is often ascribed to black hole accretion, that is active galactic nuclei of quasars. But I will show that this simple scheme is actually oversimplistic, and that the scenario is far more complex than this one, and I'll try to explain why. Now, you can have two reasons why the star formation has been inefficient in galaxies. You can have the effect on local scales, where simply the individual gas clouds have been inefficient in forming stars. You can have global effects in the sense that you have entire galaxies which have totally stopped forming stars, what is called galaxies which have been quenched or become passive. So, and this has resulted in the so-called galaxy bimodality, which is an oversimplification, but it actually works on a large statistical sample. In the sense that we know that there are galaxies that are star-forming, which are gas-rich, and which have a young stellar population, and another class of galaxies which are passive, quiescent, with little gas content and older stellar populations. And the question is why some galaxies at some point stop forming stars and transform from star forming into passive. That is what, and the basic question is what is the mechanism which is responsible for quenching star formation in these star forming galaxies and responsible for this transformation. Now, to put this in a more quantitative context, this is often this bimodality is often shown in this kind of diagram, where you have on the y-axis the star formation rate, and on the x-axis the stellar mass of galaxies. And these are contours showing the distribution of several thousands of galaxies, in this case from the Sloan survey. And you see that the bulk of star-forming galaxies are distributed in this relatively tight correlation, which is often referred to as the star formation main sequence. But you have this additional population of galaxies which, for a given stellar mass, are much more have much lower star formation rate, and in many cases they don't even actually show any evidence of ongoing star formation. And so the question is why some galaxies at some point decide to stop forming stars and migrate to the quiescent population. Stars form out of cold gas, so understanding why in some galaxies you have star formation and in others you do not translates into understanding the behavior of gas, and particularly whether you have understanding the amount of cold gas that you have in galaxies and the efficiency with which cold gas can form stars. And this is essentially summarized in this diagram here, which is what is commonly known as the Schmidt-Kennigan relation, and showing that the surface density of star formation in disks, in galaxy disks, is related to the surface density of gas, and primarily the surface density of molecular gas. Therefore, you can understand that in order to quench star formation in galaxies, you have two possible ways. One is to reduce the amount of gas, okay, which can happen through removal of gas, ejection of gas, or the simply consumption of gas, that you keep using gas for forming stars and therefore you reduce the amount of gas. Or the other possibility is to reduce the efficiency with which gas forms stars. So you keep the same amount of stars, but somehow you prevent it, this gas is prevented from forming stars, all right? And so we'll try to see which of these two mechanisms is at work in the process of galaxy quenching. Now, however, before we go into that, it's important to understand that galaxies do not have a given amount of gas and that's it. They keep accreting gas from the circumgalactic medium, and this is nicely illustrated, for instance, by this cosmological simulation, where you have on the left side the distribution of dark matter, and on the right side the distribution of gas. And you see that in these central galaxies, that is gas is being funneled through the dark matter, the cosmic streams, primarily driven by dark matter filaments, which are crossing at this intersection in this overdensity of dark matter. And the funneling of the accretion of gas through these filaments keep the formation of stars ongoing on long periods, okay? However, this is of course a simulation, but regardless of simulation, we know that galaxies accrete gas also based on observations. For instance, for the Milky Way, we know that the halo of the Milky Way hosts several so-called high-velocity clouds, and this is illustrated in this map of the sky around the galaxy, and some of this stream of high-velocity clouds are likely going to accrete onto the galaxy. And we do see events of accretion onto other galaxies also by mapping, for instance, atomic hydrogen through the 21 centimeter lines in these couple of cases. So gas keep accreting on galaxies, okay? So in order to suppress or quench star formation in a galaxy, you have therefore three possible mechanisms. One is to remove gas, either through outflows, or in some cases we'll see, for instance, through run pressure stripping, or you can suppress star formation through starvation. That is, you prevent somehow gas from accreting onto the galaxy, or for instance, you keep the halo of the galaxy hot, and therefore you keep the surrounding circumgalactic medium in a status that prevents it from cooling and accreting onto the galaxy, in which case the galaxy still can use the available gas to form stars, but once this available gas is completely used, the galaxy dies simply because of starvation, as the name says. Or the other possibility is that you do have, you keep having gas in the galaxy, but you, as I mentioned, you keep this gas in a status that prevents it from cooling and collapsing, gravitational collapsing, and which can be to form stars, which can be, for instance, achieved through turbulence, heating, or various other mechanisms. So let's take a look at these various possible mechanisms and see whether they actually happen in galaxies. Let's start with the gas removal, primarily through outflows, which is often referred to as the ejective feedback mode. Now, the most known, common and known for which has been studied for several years are outflows from galaxies driven by supernova explosions, especially in galaxies which are experiencing enhanced star formation rate, the so-called starburst galaxies. And this is clearly seen in this very nice picture of MET2, the closest of these starburst galaxies, where you have that the cumulative explosion of multiple supernovae has produced this, has piled up to produce a super bubble of hot gas that has exploded in bipolar outflows. And you see this in this hot phase of traced by the X-rays, and also in these outflow also tracks where there are also cold gas, and which, because we see this outflow also in molecular gas and in the mildly ionized gas. And however, these kind of supernova-driven outflows are not particularly effective it seems, in quenching star formation. And this is, for instance, illustrated in this simulation, where you have on the left the gas density and on the right the gas temperature. In this simulation, where top you see the face-on distribution of gas in this galaxy, and the bottom is the edge-on view. And you see all of these flickering and individual supernova explosions that are exploding, and when they pile up together, they result into super outflows, which is exploding out of the galaxy, which is impressive and has a major effect in the central region of the galaxy. But you see that the bulk of the gas in the galaxy actually is not significantly affected by this cumulative effect of supernova explosion. And the reason is primarily that this energy leaves the gas injected by these supernova explosions, leaves the gas, the disk, preferentially along the direction of least resistance that is perpendicular to the disk, and doesn't affect the bulk of the dense gas. And we see this effect of not significant efficiency in quenching star formation in this in studying the observationally in studying the outflows, and particularly the molecular outflows in star forming galaxies, because molecular outflows, because most of the generally most of the outflowing gas is in the cold molecular phase. That's where most of the mass of the outflows is found. And you see here, you have the molecular outflow rate as a function of the star formation rate for a number, and focus now on the stars, which are the starbursting galaxies. You see that the outflow rate is or the order of the star formation rate, and often lower than the star formation rate, which means that, yes, the outflowing gas resulting from these supernova explosions helps in the depletion of gas in galaxies, but not significantly more than the star formation rate. And you may think that you need actually extreme starbursts to drive really massive outflows, which can really clean galaxies of their gas content. But that's actually not true. You can see this in this most distant starburst galaxy, which is the most distant for which we could trace a molecular outflows, in this case by using ALMA to trace this blue shifted absorption of water, which is tracing outflowing molecular gas in dense gas along our lines of sight. And from this, we can estimate the outflow rate. And you see that even this, which is the most extreme starburst for which we have traced these molecular outflows, the outflow rate is actually relatively modest with respect to the star formation rate. So it's not actually that these supernova-driven outflows are particularly effective. However, you see that these other galaxies with diamonds, which are those which are hosting an AGNs, so the supermassive accreting black hole, they actually do have often an outflow rate which is significantly higher than the star formation rate. So the presence of an AGN actually can boost the outflow rate by a large factor. And you can see, for instance, in this case of this quasar at redshift 3, where the outflow rate is about 2 orders of magnitude larger than the star formation rate. So it can, in this case, the outflow rate can have a major impact on the galaxy. And this is somehow expected also on simple theoretical arguments, because we know we can estimate, for instance, what is the energy injected into the ISM or into the circumgalactic medium by the cumulative energy released by black hole accretion, assuming in this with this formula here that the efficiency is about 10%. And you can compare this with the binding energy of the galaxy, which can be approximated by this equation here. And by since black hole mass is about 1,000th of the galaxy mass, you can easily derive that the cumulative energy injected by the black hole accretion across the whole formation of black hole is about 2 orders of magnitude larger than the binding energy of the galaxy. So in principle, black hole accretion can have a catastrophic effect on its own galaxy, in the sense it could completely unbound it. The reason why it doesn't, as we will see, is that the coupling of the outflows and the energy which is injected into the interstellar medium is relatively low. But you can understand that even if only a few % of these energy is coupled with the ISM, potentially can have a dramatic effect. Okay. Now this is an artistic image of what can be could be an outflow driven by a quasar-driven outflow, and which is often accompanying various space release whenever we find these kind of supermassive outflows. But actually, it's not far from what we actually see in observations. This is, for instance, an image, a map of the nearby AGN, or low luminosity quasar, which has been obtained by using MUSE, the integral field spectrograph at the Very Large Telescope, where you have that in orange you have the H-alpha emissions tracing star formation in the circumnuclear region, and in green you have the oxygen 3 emission, which is tracing the outflow generated by the AGN, which is actually resulting in this very nice bipolar outflow. However, the most impressive results have been obtained in the last 10 years by targeting the molecular traces and finding that actually quasars drive also massive molecular outflows. And this is much more important because in the molecular phase there is, as I already mentioned, there is much more mass typically than in the ionized phase. And by tracing these molecules, for instance, like carbon monoxide, by using powerful interferometers such as ALMA, we could infer that the quasar activity can drive outflows with rates which are even of 1,000 solar masses per year. This is, for instance, the case of Markarian 231, which is the closest quasar to us. But we could use other traces, such as this transition of ionized carbon, to trace cold outflows even in the some of the most distant quasars that are at redshift higher than 6. In these cases, you see that you see a high velocity gas on scales of tens of kiloparsecs, and with outflow rates which exceed a few thousands solar masses per year. So it's quasars can really drive supermassive outflows and really energetic outflows, which can really affect the evolution of galaxies. Okay. So this is certainly one mechanism through which gas can be ejected out of, through which the gas can be ejected out of galaxies. But there is yet another mechanism, as I mentioned, that is ramp pressure stripping, and this happens typically in the densest region of galaxy clusters. We know that in galaxy clusters there is a lot of hot gas, typically best traced by the X-rays. And when galaxies plunge into the central region of galaxy clusters, they, of course, the stars don't feel any effect because they are like stones going through Earth, but the gas start suffering from the ramp pressure stripping, which initially we thought was affecting only the outer parts of galaxies, the gas loosely bound to galaxies. But more recent observation with ALMA especially have shown that actually ramp pressure stripping can actually remove even the cold gas, cold molecular gas in the inner region of galaxies. So actually can remove the bulk of the gas from galaxies and therefore again quench star formation simply through this effect of gas removal. Right, now let's see what about starvation. This is often referred to as delayed or preventive feedback. Delayed because, of course, once you starve the galaxy, the effect of quenching is delayed because the galaxy can still use the gas which is available to form stars, and preventive because, of course, you prevent further star formation once you isolate the galaxies from the fresh gas supply. Okay. Now, finding evidence for starvation is very difficult because it's difficult to find evidence for gas accretion, and therefore it's even more difficult to find the evidence for lack of gas accretion. Okay, but there have been a number of studies which have actually been very successful in investigating this. I think the most clear evidence has been in a cluster of galaxies or around the central galaxies in massive central galaxy around in the center of galaxy clusters. And here you see that the case of this galaxy cluster where the X-ray, the blue light is, the blue image map is showing the X-ray emission, which is tracing a hot gas which is in the process of cooling and therefore emitting strongly in the X-rays. And if you didn't have any additional injection of energy into the surrounding intracluster medium, this gas would cool very rapidly and accrete to the galaxy to fuel a lot of star formation, which we do not see in the central galaxy. And the reason why this isn't happening is because the black hole at the center of the central galaxy is injecting energy into the circumgalactic medium through radio jets, which results, which we can see through the radio emission. And if one estimates the amount of energy injected into the halo by these radio jets, these more or less compensate for the cooling that is observed in the X-rays, and not only in this cluster of galaxies, but actually in most of galaxy clusters. And this has been a very nice evidence that actually the central black hole through these mild accretion phases can actually prevent gas accretion by injecting energy into the halo. When this mechanism was first proposed, I was sort of very skeptical about it because I couldn't understand how, because the injection of energy through radio jets is very anisotropic, very directional. So I couldn't understand how the halo in other regions of the gas in other regions of the halo could actually be affected by this injection of energy if they were far from the radio jets. But actually, the answer to this came from these images like this one, which are impressive. This is still an X-ray image in a galaxy cluster, like Perseus, where the smooth component of X-ray emission has been removed, and essentially it has been passed through an algorithm that can detect steep gradients in the emission. And it reveals these very nice ripples of gas emission, which essentially trace sound waves which propagate across the entire halo. So although the radio jets inject energy in a specific direction, the resulting sound waves transmit this energy across the entire halo, and so it's actually effective in heating the entire halo. So that's why these, although the injection energy is anisotropic, the resulting heating is actually more or less isotropic. So this, I think, has been one of the most beautiful results in these fields. However, the radio jets are present only in a small fraction of galaxies, and so one wonders whether other mechanisms can help in heating the halo. And actually, even normal galactic outflows, especially those powered by quasar accretion, can actually be very effective in heating the halo. And this is shown, for instance, this simulation here, where this bipolar outflow generated by the quasar-driven wind heats the surrounding halo to temperature above 10 million Kelvin, and also not only this in the direction of the outflow, but also again the energy propagates more isotropically in the surrounding regions by keeping the halo with temperature above 1 million degrees. So it's also regular outflow, which are much more common, can actually be very effective in heating the halos. And to illustrate that this mechanism is actually one of the primary mechanisms in quenching galaxies in cosmological simulations, this is yet again one of these simulations where in the top left panel you have the distribution of galaxies in these large case structures. In the top right you have the distribution of gas density, and in the bottom left you have the temperature of the gas, where you see that these multiple explosions are essentially due to the events of gas accretion onto the black holes. And so during these quasar activities, they release this huge amount of energy through outflows into the halo. So on the one hand, you have this ejective phenomenon, but also, most importantly, this heating of the halo, which contributes to this starvation effect, okay? What about the star formation efficiency? Well, you may say, since there is a Schmidt-Kennicutt relation which relates the surface density of gas to the star formation rate, you may say all galaxies have the same efficiency or in forming stars. Well, that's not true, because simply galaxies with low star formation efficiency have been more elusive and more difficult to observe in the past. But they, especially with the new facilities, growing evidence for galaxies which are well below the Schmidt-Kennicutt relation have become more easy and more common to be observed. For instance, this is a relatively dull galaxy which hosts a weak AGN, which has a large amount of molecular gas, but despite the large amount of molecular gas, the star formation rate is very low. And so why this gas is prevented from forming star was initially not clear, but it's becoming more clear that probably the presence of even weak radio jets can play a role. Indeed, this galaxy has a weak radio jet, and this may actually inject enough turbulence and heating in the gas to keep the molecular gas in a configuration that prevents its gravitational collapse. And this has become even more clear more recently with some more observational evidence, especially with the MUSE instrument again. So this is, for instance, a galaxy with which hosts a weak AGN, and it was observed with the MUSE, again this integral-field spectrograph at the Very Large Telescope. And what you see here in contours is the emission of radio emission associated with the weak radio jet. In color, you see the emission of the oxygen tree line, which is essentially distributed along the jet, and this is not surprising, we've seen this several times. But the really surprising thing is that when you look at the velocity dispersion, it's actually not primarily the excess of velocity dispersion is not along the direction of the radio jet, which is what we were naively expecting, because that's where the gas is mostly stirred, but actually perpendicular to the jet in the ISM surrounding the jet. And this is actually, although initially surprising, was actually what was expected exactly by hydrodynamical simulations. Because what happens is that when the jet tries to escape the ISM of the galaxy, in doing so, inject energy 4 pi across the entire ISM, and therefore it propagates this turbulence, in particular in the galactic disk, and in doing so, on the one hand, you have both heating of the gas, but most importantly, it increases the turbulence and velocity dispersion, and therefore, if you're familiar with the tumor stability parameter, which determines whether the gas can collapse to form stars or not, becomes actually larger than unity, which means that the gas actually becomes gravitationally stable, and so it doesn't form stars. So you may say, okay, this applies only to when you have in a jet, but keep in mind that even galaxies which are AGNs which are classified as not radio loud, radio quiet, they typically also have a weak AGN, even if they are radio quiet. So these mechanisms actually can be relatively common. Okay, so we have seen that there are various quenching mechanisms in place, and there are various culprits and various actors which can be responsible for these mechanisms. And I've tried to map all of these effects in this cartoon here, where here you have the various mechanisms responsible for, could be potentially responsible for quenching star formation, such as gas removal, so this ejected move, star formation efficiency suppression, and starvation. And here you have the what is the culprit, the cause of these mechanisms. So it could be, for instance, black hole accretion, and we have seen that black hole can generate outflows and therefore remove gas, can introduce gas turbulence, therefore suppress star formation efficiency, and can heat the halo, either through radio jets or and we have seen then that the environment in which galaxies live can also have an effect in terms of gas removal through ramp pressure stripping. That is, galaxies that plunge into very dense environment can have their gas removed through ramp pressure stripping. And you can have also the effect of so-called strangulation, which I haven't had time to discuss, but actually can be much more important than ramp pressure stripping. Is essentially this phenomenon in which the galaxies still keep their gas content when plunging into an overdense environment, but the gas in their circumgalactic medium is removed. So you remove the fresh gas which can accrete onto the galaxy to foster additional star formation, and therefore you result into a scenario where you actually the satellite galaxy which accrete onto the overdense environment actually can result into dying for starvation, okay? And actually this phenomenon seems can happen in relatively mild environment, in contrast to ramp pressure stripping, which requires very dense environment at the center of cluster, can actually be much more common than ramp pressure stripping. There are other phenomena that, such as morphological quenching and gravitational shock heating, which I don't have time to discuss, but I have reported here for completeness. Now, there are entire conferences discussing all of these mechanisms and with people arguing which is more important, which is dominating in some galaxies and so on. And the answer is that all of them are actually taking place, happening. And I have shown several examples of these various mechanisms and causes. The question is whether there is, in the broader population of galaxies, whether there is statistically a dominant cause or a dominant mechanism which actually is responsible for quenching. And to investigate these, you need large statistical samples because you want to overcome the local weather of the local peculiarity of individual galaxies. Okay, and we have attempted to do this, we and several other groups, by using again large samples of galaxies. And we may start to focus on the cause of quenching, whether which of these can actually be the dominant responsible mechanism for suppressing star formation in galaxies. And for doing this, we have exploited a lot the recent survey MANGA, which is a survey of about 10,000 galaxies, for which we have integral field spectroscopy. Okay, so each galaxy has a spectral cube for which you can infer a lot of information in each region of the galaxy. So the upper panels are some examples of the stellar light distribution in a few of these galaxies. And you have, of course, in terms of information, you have millions of spaxels, so a lot of individual spectra corresponding to individual star forming to individual regions of these 10,000 galaxies. Okay. For each point, you can infer the star formation rate, therefore the surface density of star formation rate, and the surface density of stellar mass. And you can construct, therefore, diagrams such as this one, where you have the star formation rate surface density on the y-axis and the surface density of stellar mass on the x-axis. So it's similar to the diagrams that I showed at the beginning of my presentation, where you have the integration star formation rate versus star formation rate, but in a resolved way, okay? And similarly, you have a resolved main sequence of star formation and a population of quiescent regions of galaxies where the star formation has been suppressed, okay? And each galaxy can be entirely star forming, entirely quiescent, or you can have a combination of both star forming regions and quiescent regions. And you can now ask what is the mechanism or the property of the galaxy which makes each individual region quiescent or star forming, okay? And particularly, what is the mechanism that makes a region devoid of star formation? And you can explore all possible properties, stellar mass, halo mass, surface density locally, and so on. And what we have found is that the common property of all quiescent regions is that they all have a large black hole mass. And this is shown here, where you have this, again, the same diagram, but where now all the cumulative regions, the average regions, are color-coded by black mass of their central black holes. And you see that all galaxy or star forming regions, galactic regions which are quiescent, all have a black hole mass which is much larger than the region which are star forming. Okay, you may say, how do you know it's black hole? The whole mass correlates with everything, correlates with the galaxy stellar mass, with the halo mass. Okay, but you can, when you have such large statistics, you can actually verify these through various methods. For instance, you can plot diagrams like these, where you have black hole mass as a function of stellar mass, and here you are color coding as a fraction of quenched or passive galactic regions. And you see that for the given stellar mass, the probability of having a quiescent region is strongly dependent on black hole mass, and vice versa. If you have a fixed black hole mass, the probability of being quiescent depends very weakly, or if anything, on stellar mass. Same story for halo mass. So black hole mass seems to be the dominant element that is predicting the fact that a region is quenched or not. And of course, these are two projections of a three-dimensional space. And actually, there are many more galactic properties, such as the environment in which they live, the surface density, and so on. And of course, you struggle to examine this kind of multi-dimensional intercorrelations, and to make further progress. The only way is to exploit artificial intelligence, because although human mind has difficulties in wandering the multidimensional space, artificial intelligence can actually still disentangle the various contributions in a relatively effective way, especially when the statistics is very high. And so that's what we have done. And we have used one of these artificial intelligence methods, which is called the random forest, which essentially takes all the possible parameters associated with the galaxy, both global, local, environmental, such as black hole mass, velocity dispersion, surface density of stellar mass, halo mass, bulge to gas disk ratio, metallicity, overdensity, and so on, and identify which of these parameters is the most predictive in associating in defining that the region of the galaxy is actually passive and quiescent. And the one that is still the dominant one is the black hole mass estimated from the central velocity dispersion. And this actually is true only for central galaxies, and for high mass satellite galaxies, typically with masses above 10 to the 10th stellar mass, which is actually the bulk of the population in our sample. But summarizing, so if you want to identify one primary parameters of galaxies that is responsible for quenching the entire galaxy or even regional galaxies, this is the black hole accretion that as a result of this is integrated activity, integrated accretion into the final black hole mass. So it's surprising that to me, because it means that regardless of the various parameters of responsible for the evolution of the galaxies, the black hole mass and therefore the integrated black hole accretion is the one that is primarily responsible for the quenching of the galaxy. You can expand the same kind of analysis for low mass satellite galaxies, and I don't have time to go through the same process, but you see the result here in these light shaded histograms, where now the black hole mass, which was the dominating predictive properties for massive and central galaxies, is actually not the least important, one of the least important now, while now this parameter delta phi, which is tracing the galaxy over densities, becomes suddenly the most important. So in this case, for low mass satellite galaxies, the environment in which galaxies live, in particular the overdensity of galaxies, is actually the most important in driving galaxy quench. So environment is in this case queen in determining whether a galaxy is quenched or not. You now may want to wonder which of these mechanisms is actually most important in quenching galaxies, regardless of which is the cause. And we have investigated, so gas removal, star formation, suppression, starvation. We have investigated this by using the metallicity of galaxies. You know that the formation of elements heavier than helium are produced in the interior of stars, and there is explosive events and released into the interstellar medium and recycled by further generation of stars, so that you expect that the newer generation of stars are more and more metal rich. And you may wonder, why does it have this to do with the quenching? Well, because when you have supernova explosions, these can produce outflows and therefore result in loss of metals, while gas accretion can actually dilute the metallicity And since both outflows and accretion are, we have seen important mechanisms in galaxy quenching, this actually the metallicity helps to shed light in what are in which of these processes is relevant for the quenching of star formation in galaxies. And you can derive the metallicity from the stellar population, based from the spectrum. And these diagrams, this cartoon illustrates how we can obtain some information on the quenching based on the stellar metallicity. So when you have a galaxy which is forming stars and while accreting gas, you have that you increase the stellar mass, you increase also the stellar metallicity because galaxies keep releasing star formation keeps releasing metal into the interstellar medium, which is being recycled. But the metallicity doesn't increase by a large factor because it keeps being diluted by accretion from the intergalactic and supergalactic medium. If you remove the gas and you stop star formation, then what happens is that the galaxy evolves in a passive wave into a quiescent galaxy, and the resulting passive galaxy has the same metallicity as the star-forming progenitor. In the case instead of starvation, when you stop the inflow of gas, then the galaxies keep forming stars with available gas. And in this case, the metallicity actually can increase much more because it doesn't have any longer the dilution effect by the accreting pristine gas from the supergalactic medium. As a consequence, what you expect is that the resulting passive galaxy has a stellar metallicity which is much higher than the star-forming progenitor. And we have tested these by using, again, a large sample of spectra of thousands of galaxies. And this is show the average stellar metallicity of local passive galaxies as a function of stellar mass, and compared with the metallicity of the star-forming local galaxies and the star-forming progenitors at higher redshift. And you see that there is this gap in metallicity, which is a clear signature that the quenching of these passive galaxies must have involved an extensive period of starvation. This is not enough. If you do a detailed analysis, you figure out that starvation is not enough. You also need an ejective effect because otherwise you end up still with an amount of gas which is too large with respect to what we see in passive galaxies. So you must have still a combination of ejection and starvation. What about star formation efficiency? This has been investigated more extensively in the last years, and by using especially data from gas content from ALMA and other galaxies and other facilities, but and also using other techniques such as other traces of the gas content, such as dust extinction, and that's what we have done in this diagram here. So what you have here is the star formation rate. Again, the same diagram is here. Star formation rate is a function of stellar mass, where now the color coding is tracing the gas fraction, therefore the ratio between gas mass and stellar mass. And in the bottom diagram, the star formation efficiency, that is the star formation rate per unit gas mass. And what you see is that, again, this is based on data from thousands of galaxies. What you see is that as galaxies leave the main sequence and going towards the quiescent region, they both decrease the gas content, both probably because of gas removal and because of gas consumption. But in doing so, they also decrease the star formation efficiency. So the little amount of gas that is left is also less effective in forming stars. So you have a combination of both gas depletion and star formation efficiency, which contributes to the quenching of star formation. So if you have now we had to identify what is the dominant effect, the dominant mechanism in suppressing star formation here. We don't have a specific queen or queen, but actually all three effects, gas removal, star formation suppression, efficiency suppression, and star formation, all play a role in this quenching. So summarizing, the process of galaxy quenching, there are a broad range of possible causes and mechanisms. But if I have to identify some big picture, I would say that for central galaxies and high mass satellites, the main culprit is the integrated effect of black hole accretion. And the way it happens is probably that the quasar-driven outflows are produced by the quasar accretion, by the black hole accretion in the quasar phase is injected into the ISM, but most of the outflow escape along the least resistance path. And so you have some gas ejection, but also a lot of heating of the halo through these outflows, but also through jets, which eventually results in starvation of the galaxy. And also at the same time, you have injection of turbulence and heating into the interstellar region, which reduce the star formation efficiency. On the other hand, for low mass satellites, what happens is that for these galaxies, the main effect is that as they plunge in the overdense environment, they lose their circumgalactic medium, although they keep still most of the interstellar medium in the galaxy, and this is shown in this nice simulation, both for the case of the group, galaxy group, and the case of galaxy cluster. But losing their circularity medium, they lose the source of gas for further rejuvenation and accretion, formation of stars in galaxies, and therefore, in the end, the galaxy die as a consequence of starvation. So this is the big picture. You may say that we have a rough understanding of the quenching mechanism in galaxies, but keep in mind that most of this information that I showed to you is actually resulting from observation of local galaxies. And what you want to do in the future is to push towards a higher redshift and understand these quenching mechanisms when they actually are the most important, that is close to cosmic noon, or even close to the earliest phases of galaxy formation, because we know now that there are passive galaxies already in place by redshift 2 or even 4, so this quenching mechanism must be already effective in the earliest phases of galaxy formation. And so some of the prospects in the near future to investigate these quenching mechanisms at high redshift are certainly again ALMA, the Atacama Large Millimeter Array, and this is being used to investigate certainly the gas content in distant galaxies. But I think the most interesting prospect is to investigate detect the halo heating through the via the Snyder-Dobby effect, because tracing this halo heating is actually very difficult through other methods such as X-ray emission, because in the distant universe you will need very high sensitivity. However, through the Snyder-Dobby effect, this is becoming possible. It has been already investigated, for instance, by using stacking of data from CMB experiments along the line of sight of quasars, and there is some detection of some SD effect associated with the halo heating of quasars. However, these are very difficult to experiment because the beam of CMB experiment is very large, and so include the emission of also the dust emission in galaxies. While with ALMA, it will be possible, it is already possible, and there are some preliminary results, to detect the SD effect on the individual galaxies. Of course, ALMA is also powerful in detecting the cold outflows in the early universe. I showed you some examples in the beginning of my presentation, but those are actually, we have examples of these cold outflows only for a handful of galaxies, while to get a more statistical investigation, we need to stack a lot of quasars or galaxies, but in the future it will become possible through more extensive surveys to actually detect these kind of outflows in individual galaxies at high redshift. Then the other, of course, important facility will be the James Webb Space Telescope, which is often regarded as the successor of the Hubble Space Telescope. And this will have a sensitivity which is orders of magnitude in some bands higher than local current facilities, and will allow us to investigate for instance, the ionized outflows in the early galaxies. This is, for example, a simulation of ionized outflow generated by quasar at redshift at around 6. It will be possible to investigate the chemical enrichment all the way to the earliest epochs, and therefore perform a similar analysis to what I've shown you in my presentation, but at a much higher redshift, and also tracing the presence of the first passive galaxies, and see actually when actually quenching has happened in the universe. Finally, while James Webb is fantastic in terms of sensitivity, is actually not the optimal machine to investigate the environment, because to study environment that is large-scale structure and so on, you need actually large area and to trace the distribution of hundreds of thousands or even millions of galaxies. But for this, it will be possible to use moons, the next generation optical near-infrared multi-object spectrum of the Very Large Telescope, which will be able to obtain simultaneously spectra of 1,000 galaxies simultaneously. And most importantly, in the near-infrared, where most of the diagnostics to trace the physical properties of galaxies are shifted at around cosmic noon. And in this way, it will be possible actually to trace by obtaining the deep spectra of millions of galaxies around cosmic noon, to trace the environment in which galaxy lives and the properties connected with the environment, and therefore trace galaxy formation and transformation as a function not only of cosmic epochs, but also as a function of environment in which galaxies live, and therefore determine whether environment already plays a role in quenching galaxy formation, star formation in galaxies already in the early universe. And I will stop here. Thank you.
Thank you, Roberto, for this amazing overview. You've shown a lot of fantastic results and also beautiful perspectives for the future. So I'm sure there must be many questions for you. I see already one raised hand by Fabio. Fabio, you can go ahead.
Yes, Roberto, it's Fabio speaking. Could you please tell me, I missed that, how did you evaluate the black hole mass in the black block yourself paper?
Yes, so it's based primarily on the central velocity dispersion, and which is, if you want, an indirect tracer, but it's the best tracer of the black hole mass. It's the one that correlates most tightly with the black hole mass. There have been also studies which actually have investigated the galaxy quenching by using more direct dynamical measurement of the black hole masses, which gives the same result, that is, the quenched galaxies have a higher black hole mass than star-forming galaxies, but of course with the statistical significance which is much lower than what achieved with these studies. That is the power of having so many galaxies, hundreds of thousands, tens of thousands, is that you can also explore the disentangle the dependence from other galaxy parameters such as environment, surface density, and so on.
Thanks.
And, oh, I see. Hello, do you hear me? I have unfortunately some problems with my net. So are there other questions for Roberto or comments?
Adriano is raised.
Thank you, Angelo. Okay, Adriano, go ahead.
Ciao, Roberto. First of all, many thanks for your very nice talk. I have a number of questions, actually. Let me just ask two. One is when you have shown the outflows from quasars that are especially at high redshift, or in general, can you estimate the fraction of AGNs where the outflow is detected, or let me say, what is the fraction of AGN where you expect the outflows to be detected and you don't see? So the question is, how common is this outflow among quasars? I know it's a tricky question, but what is your
is a
feeling?
subject of trillions of proposals.
Yeah, I know. But
I would say that the evidence for ionized outflows is nearly ubiquitous. So you nearly see in some form or another nearly in all quasars. So the question is that typically the fraction of energy and mass in ionized outflow is a small fraction, and therefore although this is still debated, therefore a lot of effort has been going into trying to identify the cold phase of outflows, which is where most of the mass is expected to be. And individual detections at high redshifts are very few, but we think it's mostly a question of sensitivity. And moreover, since these observations are done through interferometry and the outflows are extended, often the failure to detect these cold outflows is often not only because of sensitivity, but because of lack of sensitivity to extended emission. So a lot of people have been spending 10 hours or several hours in a very high resolution, and so filtering out all of this extended emission. So it is all of these technicalities that play a role. Through stacking has been a lot employed to try to give an average assessment of the prominence of how common outflows are in quasars, cold outflows, and there is a clear detection of high velocity cold gas in the average static spectrum of quasars, but the result is that the strength of the outflow in terms of outflow rate or energy actually is not that high, and is confirming that the ejective mode is not so doesn't seem to be so efficient in actually quenching star formation. And actually, most of the energy produced by these quasar-driven outflows doesn't result into a significant ejection effect, but probably mostly into a heating of the halo and therefore in the starvation effect.
I don't know if I may have another question. In your explanation, how do you explain the correlation between the quiescent fraction and the morphology? So how most of the quiescent galaxies turn out to be elliptical at the end?
Well, this is a misconception, if I may, in the sense that it is this association of morphology and the quiescence is actually, when you look at the more recent data and so on, a large fraction of passive galaxies are actually disky, okay, and are actually rotators, are not dispersion dominated, especially as you go to lower masses. And this is perfectly consistent with being, how to say, having quenched as a consequence of starvation, in the sense that simply the star formation has simply faded across the entire disk and made everything more fainter across the entire disk. And the fact that many of these galaxies are more bulgy often is a consequence of a fading effect of the disk. As the star formation stops in the disk, it becomes less luminous, and so the bulge becomes more prominent. So you tend to have a different, more spheroidal morphology, but often is a question of relative contrast. Okay, but it's true anyhow that at very high masses you do have predominantly really spherical, well, elliptical-like and velocity in the specially dominated galaxies, but in the very mass end. And there is actually can simply be that the quenching is accompanied by morphological transformation through merging, where you have merging that feeds the black hole along as with the galaxy transformation, and the effect of black hole accretion also results into quenching through ejection and halo heating. So the two things can actually go hands together. Is actually one has to be careful in I agree that there is this effect also of morphological transformation, but one has to be careful not to overstate it because sometimes it's overemphasized.
I think we have time for just 2 short questions, and then we need to switch off. Fabrizio?
Yes, hi Roberto, very, very nice presentation. And I think, I mean, it has been clear from your answers to the question that you really believe more in starvation than other things. And I tend to agree. I really like your talk. And talking about starvation, I think you made clear the point that one important thing to do is actually to detect these hot halo, especially at high redshifts. And this is, as you said, I mean, it's not doable in the X-rays, not even in 50 years from now. So
no, with Athena, I think is maybe.
I can do some, but no, right. But my question is actually because SZ is definitely okay if you just want to know whether there is hot gas. I mean, the temperature of the gas. But if you want to study also the metallicity, you need to detect some element in these halos. And I was wondering, but I have no idea whether this is feasible, whether a possibility could be emission line from spin flip hydrogen-like ion, like oxygen or nitrogen. There was this old paper by Tsunayev about this effect. I mean, it's like the 21 centimeter line for hydrogen, but for hydrogen-like nitrogen or oxygen, which would be in the radio band, but I don't know what is the sensitivity to do.
I don't know. It's very nice. I think I already heard this, but I don't know in terms of sensitivity whether this is actually possible. Keep in mind that we are already struggling to detect the SZ.
No, I know.
So I think it's a step further. But I don't know in terms of detailed sensitivity how feasible is that.
So I think we can have a last question from Alberto.
Yes, thank you, Roberto, for excellent talk. In fact, you listed, can't remember how many physical processes, more or less, one independent from the other, various causes, various mechanisms. What always struggles me is to understand the regularity of the stellar mass function for galaxies. And just to give you an example, you know the mass of the supermassive black hole in our galaxy, which is 4 orders of magnitude or more or less than the supermassive black holes in other galaxies. And still, the mass function is not, from these two kind of population, is not so different. Certainly not by 4 orders of magnitude. All this puzzles me a lot.
Yeah, that's true. Now we are going to technicalities of the scaling relation of black hole masses with galaxy properties, and particularly whether you have the pseudo bulge, the bulge, and whether you should select have 2 different correlations for different classes of galaxies. And that may be actually, you're absolutely right, that may be the next steps to investigate this kind of correlations and the predictivity of this galaxy, in particular the black hole mass. It's not simple because in this statistical analysis, to have it sound, you have, whenever you increase a new parameter, I think, to explore it, you have to increase the statistics by nearly an order of magnitude. So you understand that the more you split the multidimensional properties of galaxies in more properties, it becomes more and more tricky for even for artificial intelligence to disentangle the various properties, but it may become possible actually, and we can certainly explore that. Yeah.
Okay, so thank you, Roberto, really, and thank you all for having attended this meeting. Now I will ask the attendants to leave the room, and Roberto will be left alone with the PhD students. So we ask Roberto another, 20 minutes to spend with us, if it doesn't, he doesn't mind. And so I invite you all for the next Quidulta colloquium in a few weeks. So thank you all for having attended this beautiful seminar. And if you want, you can join me in giving Roberto an applause, a virtual applause. And of course, Rob, you are invited to Rome whenever you want to come, really in person.
As soon as possible.
Okay. Okay. So, so while people, I think.
Ciao, thanks. Ciao.
Ciao.
Ciao Roberto, thanks.
Ciao Roberto.
Sì, credo che stiano più o meno andando via tutti. Grazie mille, Rob, veramente.